Hello, my name is KotyCreel, and I am a student in AST301, and I am going to give a presentation on the Nobel Prize in Physics presented in 2019 to Michel Mayor and Didier Queloz for the first detection of an exoplanet. So what is an exoplanet? Exoplanets are planets that have formed outside of our solar system, orbiting other stars. While exoplanets can orbit a variety of stars, including pulsars, most are known to orbit stars like our sun. These strange worlds have been found in many different forms. Some look like the planets within our solar system, and the others are dramatically different. 15 types of exoplanets are currently listed in the Unified Astronomy Thesaurus. 5 of the exoplanet types refer only to size. In order, from smallest to biggest, they are rocky or terrestrial planets, super-Earths, mini Neptunes, ice giants, and gas giants, and they can be divided into multiple subcategories, such as planets in the super-Earth and mini Neptune size range that may be ocean planets, having liquid water oceans hundreds of kilometers deep. Some rocky planets found in carbon-rich systems may be carbon planets, having rocks formed of compounds of silicon and carbon, different from our solar system's silicon and oxygen rocks. Hot Jupiters and hot Neptunes are big gassy planets with fast orbits very close to their stars, so close they'd be tidally locked, with a hot hemisphere permanently facing the star and a cold hemisphere permanently facing out. There are cold Jupiters and cold Neptunes as well, orbiting farther out just like the planets they're named after. Lava planets are large and super dense worlds in close hot orbits, and pulsar planets, like I mentioned before, orbit pulsar stars within their intense magnetic fields. So, how do we come to realize that all of these strange, not so new worlds existed? And how are we able to not only know they are there when we can't see them, but also know so much about them? Well, in 1995, Swiss scientists Michel Mayor and Didier Queloz announced the first detection of an exoplanet. The planet, 51 Pegasi b, is located 50 light years from Earth. And since Mayor and Queloz's detection, more than 4,000 exoplanets were discovered by the time they were both awarded the 2019 Nobel Prize in Physics for contributions to our understanding of the evolution of the universe and Earth's place in the cosmos. Mayor and Kalos challenged our preconceived ideas of planetary systems and forced scientists to revise their theories of physical processes of planetary formation. The discovery of 51 Pegasi b, utilizing the LED spectrograph, revolutionized astronomy and initiated an entirely new field, with new instruments focused on finding and characterizing exoplanets. Mayor and Kalos were instrumental in developing the radial velocity technique that is still used to search for exoplanets today. The radial velocity method for detecting exoplanets relies on the fact that a star does not remain completely stationary when it is orbited by a planet. The star moves in a small circle or ellipse, responding to the gravitational tug of a planet. When viewed from a distance, such as from Earth, these slight movements affect the star's normal light spectrum. Using highly sensitive spectrographs, scientists can track a star's spectrum, searching for periodic shifts in spectral wobbles. Here is a simulation of 51 Pegasi, and we can see the exoplanet orbiting around the star. We also see how the star follows a small orbit. This is because it is affected by the gravitational force of the planet, and the planet and the star both rotate around a common center of gravity. This creates an observable wobble, and the star is moving back and forth in the direction of our line of sight. The speed at which a star wobbles can be measured as its radial velocity, since it affects the wavelength of the light beams that we are looking at. So even if we cannot see the planet directly, we know that it must be there. This is like the Doppler effect that occurs when a sound source is moving towards or away from us. When the star is moving towards us, we can see the wavelengths become shorter and the light becomes bluer. When it moves away from us, we can see the wavelengths become longer and the light is redder. And here is a radial velocity graph of 51 Pegasi that Mayor and Kalos used to confirm an exoplanet orbiting the star. The wobble of the star is presented here as peaks and troughs or dips on the graph. Each individual point shown here is an actual measurement taken and shows the changes in wavelength as the star wobbles back and forth from the gravitational tug of the planet. The changes in color can be determined by measuring the star's light's wavelength, providing a direct measurement of its velocity in the line of sight. The amount of change is determined by this formula that tells us the observed wavelength of light changes depending on the relative velocity between the source and the observer. Since the radial velocities are extremely low, astronomers must measure thousands of wavelengths at the same time using a spectrograph. The radial velocity is usually measured using the observed Doppler shift of spectral lines given by this formula, which indicates that the change in the wavelength of light is proportional to the relative velocity of the source and the observer, divided by the speed of light. This equation expresses how the wavelength of light shifts due to the relative motion between the source and the observer. Other methods than radial velocity are being used to discover exoplanets. They are the transit method, direct imaging, microlensing, astrometry, and the timing variation method, which actually tells us more than one exoplanet is there. And here is a transit method simulation. The transit method utilizes photometry to search for exoplanets by measuring the intensity of a star's light when a planet passes in front of it while within our line of sight. This is similar to what we experience during a solar eclipse, when the moon passes in front of the sun. The transit method can be utilized along with the radial velocity method. While the radial velocity method provides the mass of the exoplanet, the transit method provides the size or radius of the exoplanet. With these parameters, we can calculate the exoplanet's density, thus determining its structure and composition. Transit photometry also allows astronomers to observe the exoplanet's atmosphere as the light from the star passes through it. Since the first discovery of an exoplanet orbiting a solar-type star, new planetary systems are not only being discovered by telescopes on Earth, but also from satellites in space. TESS has scanned 7,351 potential exoplanet candidates, with 570 confirmed. And prior to TESS, the Kepler Space Telescope discovered more than 2,600 exoplanets. Today, James Webb Space Telescope is confirming exoplanets and determining their atmospheric compositions, and there are more to be confirmed after the launch of the Nancy Grace Roman Telescope in 2027. Ground-based telescopes have also helped confirm and characterize exoplanets. They work with space-based telescopes to provide details of exoplanet atmospheres, composition, and other vital statistics. There are also a multitude of citizen science projects today, increasing the number of confirmed planets and our understanding of planetary formation. By assisting expensive space telescopes with continuous ground observation to maintain the orbital parameters that would otherwise become stale or inaccurate over time. Here is a light curve I created in a research program at ASU. Research topics in exoplanets with Professor Molly Simon and Heather Hewitt. We utilize the transit method, and you can see the dip in brightness shown here as the exoplanet is orbiting in front of its star. The data provided by this light curve allows us to provide updated and accurate orbital parameters so that space telescopes do not waste crucial time waiting for a transit, or worse, missing the transit. The discovery of an exoplanet orbiting a solar type of star began a revolution in astronomy. Since Mayor and Kalos detection, more than 4,000 exoplanets were discovered by the time they were both awarded the 2019 Nobel Prize in Physics. And with these strange new worlds still being discovered in a large variety of sizes and forms, we may eventually find an answer to the question of whether extraterrestrial life exists. Thank you.